Okay, let's get started. It's good to see you again. It's been a long time since I was here in class. Hopefully last week went well with the guest lecture on differential privacy and the video lecture. Are there any questions from last week or on the project that anybody has right now? Yes?
Do you have to calculate privacy for like your
I will put up some, I was just reviewing the slides this morning. I posted the slides from that lecture. I will put up some study questions from privacy. And so I think understanding the study questions should sort of guide you. I wouldn't expect you to sort of do the calculations at the end of the lecture, but sort of understanding the issues. And we will be talking more about privacy, I think, starting Thursday. And so there'll be sort of more privacy stuff to cover. Any other questions? Hopefully people have gotten started on this project. The first part of the assignment seems fairly clear on how to get started. The second part, several people have had questions on how to get started, and I really recommend you sort of, look at the protocol and sort of figure out exactly what the system is doing and understanding all the pieces and, which pieces are secure, which are insecure, what are the things you can change, what are the things you can reverse, to sort of figure out what your opportunities are. Like the other ones, the actual amount of code to write is quite small. It's really sort of a thinking and understanding kind of exercise. So, with that, we will begin our last lecture on network security. And what we'll be talking about today is, if you're an attacker, how do you find good places to attack? How do you know if you can attack them? And then if you're an organization that doesn't want to be attacked, what are the network level defenses you can deploy? How do they work? How well do they work? And what are the ways to defeat those network level defenses? So we'll talk a little bit about tools for port scanning, how you fingerprint a server to sort of figure out what it's running. We'll then talk about intrusion detection, and as I said before, how to avoid intrusion detection. So the first thing, if you're an attacker, is you want to find a good target to attack. So the question is, what does a good target mean? It means you'd like to find a target that has a vulnerability that you can exploit. So there's a question of how do you know what servers are out there and how do you know if they're running buggy software? So that is the first thing we'll talk about. So the first thing, suppose you want to attack a company, is you want to find out, you might want to find out either if you have a network address, who it belongs to know what company you're attacking. If you know of a company, you might want to find what network addresses it's using so you know what servers to be looking at for possible attacks. So one of the easiest ways to do this is there's a registry called Whois. Whois is a global database that says for every IP address in the world that is not put behind a corporate firewall, who owns that IP address? Because IP addresses are assigned to an organization. I mentioned before the University of Wisconsin controls hundreds of thousands of IP addresses. This means that these IP addresses, the UW gets to decide who they connect to and how they get routed. So you can use this to sort of look at blocks of IP addresses and see who they belong to. So here's an example. I looked up google.com on Whois. So 127.217. Is this the right one? This is the wrong one. I apologize, this is the wrong screen capture. But what Whois does is you enter an IP address and it will tell you who controls this. So in this case, 127.217, it says it's reserved. A huge block here is reserved. It shouldn't be in use. This block was actually in use by Google, which is a little surprising. But Whois will tell you who controls a block of IP addresses. And it'll give you some comments. It'll tell you when it was assigned to someone in 1981 and who did this assignment. So once we know about a block of IP addresses, Whois will sort of tell us who controls this block. The next thing we want to do is sort of figure out, of all these addresses in the block, which ones actually have hosts that are running. Because there might be thousands of addresses that Google controls. They might not actually have servers attached to all of them. So we want to find those servers. We then want to figure out what services are running. Are they running a web server? Are they running a DNS server? Is it running a MySQL server? Is it running something else? Once we figure out what it's running, we would like to know what version of the software it's running. Because if we know what version, then we might know what vulnerabilities there are in that version if they haven't been patching it. We also might want to know what operating system they're running. Because if we know what operating system they're running, we might know about vulnerabilities in the operating system so that we can figure this out. And so, at the same level, we'd like to sort of figure out everything we can about what a server is doing and what its vulnerabilities are. So the key question is, how do we actually go about doing this, right? Because there's a lot of information we want to get. Fortunately, someone has done all this work for you. There's a tool called Nmap, Network Map. It's sort of the de facto tool for network reconnaissance. I do not recommend you use it against anybody else because you might get some nasty letters saying that you're port scanning a company. If you talk to people doing network research, they're very familiar with getting these letters that will, administrators will send an email to the University of Wisconsin saying, somebody there was trying to scan and break into our computers. What are you going to do about it? But it has lots and lots of tools built in to do this kind of scanning. The other thing that's kind of fun is that if you watch movies about computer security, then almost always this comes up. So this is from The Matrix Reloaded, where I forget who it is sort of, scanning their computer for vulnerabilities. You might also note that I believe today is the anniversary of The Matrix coming out. So a good time to go home and watch the movie. Here's another movie where it shows up. Again, you can see Nmap doing a scan up in the top. And of course, yet another movie, This is Elysium. 100, 200 years in the future, people are still using Nmap to break into their favorite satellite colonies. So it's sort of a great, there's a reason that it shows up here. One, it prints out cool stuff and it looks technical, but it actually is sort of a useful tool to show you things. So the first thing you can do is you can say, look at a block of addresses and find all the hosts running on this address. So this command here, the first thing, -pn, says, assume all the hosts are up. So just scan every address you can find. It then says, does a TCP connection scan, which means try to connect to every port on these servers to see if there's any ports that will respond and send a packet back. Actually, not any port, but it'll do a TCP connection, and then it says connect to port 22, which is for SSH. So it'll tell you, is there an SSH server running on this machine? So this is my home network. You can see that it brought up a bunch of different machines here, and it says there's like an open SSH service, a filtered SSH service, a lot of different things. So this tool is now telling me what are the hosts on my home network that I can try to break into. Yes?
So you mentioned that how do you do this? Is this like legal? What was the letter they sent you?
I haven't gotten a letter. Does anybody know? Do you know any more about this?
At work, I've got a few letters. Basically, the letters just contain. It depends on your intent. The worst thing, but like as far as reconnaissance isn't illegal. The worst thing that's going to happen is they're going to block your IP address off your network, and that's about it, unless you take further action.
So they might filter your traffic so you can't actually connect in the future, which, but the web server you want to go to, that might hurt you. But, it sort of says, we're watching, we know that you're doing things, don't think you're going to get away with this. In some places they're very sensitive. It takes very little to trigger a letter from some places. Some places don't care because they probably get scanned all the time. Okay. So some of the status messages you might learn is whether something is open, which means it's accepting connections on this port. Whether it's closed, which means that the host is responding to somehow, but it's not allowing any connection to be created. Or filtered, which means that you couldn't get packets through on the port, which means there might be a firewall or something like that that is restricting your ability to connect. So the port is there, we can't really figure out what's going on there. So we saw some that were open and filtered on the last slide. So once you know that a host exists, the next thing you want to know is, what is that host doing? Is it running something I can break into? So what we can do now is pick a host, and we're going to pick 192.168.0.1, what happens to be my home Wi-Fi router. And we're going to see, can we break into this Wi-Fi router? So we're going to just do a straight up Nmap, which will do a port scan, and it will try to connect to all the ports on this and see what it finds. So it connects to port 22, it sees there's an SSH server. It connects to port 80, it sees there's an HTTP server. Connects to port 1900, it's UPnP, and then 20005. So it tells me there are some open services on this router, so I know, there could be some good stuff here. The next thing I want to know is, are there vulnerabilities that I can use to break into this? And so for that, I would actually like to know the versions of this software. I'd like to know what this router is running, and what software it's running so I can know whether there's some bugs in it I can break into. So Nmap can do that for you. If you patch in -sd, it will try to actually figure out which version of each service it's running. And it does this, sometimes it's easy. You connect to a server and it'll send back a string saying, I'm running, Apache HTTPD version, 4.9.12.32. In other cases, what you have to do is send a bunch of packets and figure out from the behavior of the server what it's different. Because as software changes, it behaves differently. They fix bugs, they make things faster. So by sending packets, you can sort of figure out which version of the software is running by looking at how it responds. So Nmap has that capability of sort of figuring these things out. So in this case, you can see from SSH, it's running Dropbear SSHD 2012.55 protocol version 2. It's running TP-Link Archer HTTP server. It doesn't really know about you can't figure out a version for UPnP and BTX. So what you can do then is you can say, well, now that I know what's running, let's use Google to figure out if there's any vulnerabilities. So I searched up Dropbear SSHD server, and it says there's a vulnerability here in Dropbear. There's multiple vulnerabilities. Unfortunately, they're up through versions 2012.54. They've all been fixed in 2012.55. So my initial search did not find vulnerabilities, but this is what you can do once you know what is running. So the next thing we might want to know what operating system is running, and we do the same approach. Here we look for different behaviors between different versions of an operating system. As Linux or Windows advances, there's subtle differences in timing or in what flags are set in protocols or what protocols are accepted or how things are implemented. And so by profiling those, you can kind of figure out what's going on. So if we pass the -O flag here, it will tell me what operating system it's running, and it tells me it's running Linux kernel 2.6 versions between 2.631 and 2.635. So there's sort of a couple months, maybe a 6-month window in there when this operating system could have come from. So that tells me, that likely things that were fixed in Linux kernel 4 or 3.22 are not patched in this kernel, potentially, and so there might be vulnerabilities that it can go and exploit. So that is kind of the key takeaway, is you can use whois to sort of figure out who owns an address or what addresses are controlled by your organization. You can use Nmap to then find which hosts are running on those addresses. You can then, for each of those hosts, look and figure out what ports are open, what services are running on those ports with what versions of those services, so you can find bugs, and you can figure out what operating system is running to find bugs in that. And that gives you sort of a nice sense of what kind of attacks might work on here. It also tells you what defenses there are, because, for example, we saw that some ports were filtered. This says there might be a firewall that doesn't allow traffic on this port number, and so we're not going to be successful trying to attack through that port to that application. Any questions? Yes?
Does anyone ever, for security reasons, try to make the host look like a different operating system?
I don't know of anybody doing it. You could certainly try to do it. For example, you could, in Linux, you can, in some cases, replace the TCP/IP stack with your own version. And so you can sort of change things. Most people don't. And if you think, as an attacker, you're sort of often looking for the easy targets. And so somebody who's going to go to that effort will probably do a lot of other things to make it hard. It's likely it's possible, though. I mean, certainly, simple things like running Linux inside a virtual machine on top of Windows will change what you look like. Any other questions? Okay, so that was how you scan and identify hosts. The next thing I want to spend the bulk of today talking about is how do we sort of secure our connection to the internet. So this is sort of the basic architecture a lot of enterprises and organizations look at. They have the internet. They will then have some kind of firewall or intrusion detection system, and we'll talk in a lot of detail about these. You then have sort of your outward-facing servers, like your public web servers. You then have an inner firewall that separates that web server from the rest of your sort of back-end data. And the idea is that that middle area is going to be called a demilitarized zone. And this means that it's sort of neither part of the internet nor part of the secure part of your company, but it's sort of part of your company that is accessible from the internet. And the reason to do this is that these are machines that are very vulnerable because they're accessible from the internet. They can be port scanned, they can be hit with denial of service attacks. So one, you don't want all your machines to be accessible that way, and so you put them behind a firewall. But these do need to be somewhat accessible because they're providing a service to your customers. The problem is because they're likely to be attacked, we don't want them to have access to our inner servers. And so they are accessible to the outside world, but they can't access the inside world. So that's why they're sort of in this middle ground where they can sort of access their own data, they can talk outward, hosts on the inside can talk to them, provide new data, but they can't get inside the network. So these are sort of, the troops that are outside your castle, that are protecting your castle, that have to engage the enemy, but their chances of survival are less than average. Okay, so what we want to talk about then is how do we build this intrusion detection system, and what is it, and how do we sort of build firewalls, and what do they do? So there's a couple of different services that are important to know about. One is an intrusion detection system. This is really sort of a passive monitor. Think about the passive network attacker. IDS is like a passive network attacker, only the goal is to look at all the traffic and figure out, do I see something wrong? Do I think that I'm being attacked? If I think I'm being attacked, I can raise an alert, I can notify an operator, and some human or some automated service can come in and decide how to respond. But the goal is to detect when you're being attacked, not to respond. The second thing is an intrusion prevention system. This sort of goes one more step, and it says when we detect an intrusion, we're going to do something to prevent it. If we see, we're being attacked, we are going to take some response, such as dropping traffic, responding to traffic, closing ports that we're vulnerable on, replicating our servers more to sustain a denial of service attack. We're going to do something to prevent that intrusion from being successful. And then finally, we have a firewall, which is sort of a low-level, simple intrusion prevention system that really just sort of says we're going to do a coarse-grained filtering at the packet level to say certain packets to certain ports aren't allowed through, or from certain addresses, other ports or other packets from other addresses to other ports are allowed through. So they're fairly stupid. They don't really know whether they're being attacked. They just say, we know we should only let certain kinds of traffic through. There's then sort of two broad categories of intrusion detection system and intrusion prevention systems. One is what is called signature-based. And it says, the idea here is we know lots of existing attacks out there. We've seen them before. So somebody will create a signature that says, here is how you recognize the attack. So for example, in the buffer overflow attack that you implemented, somebody might say, well, we know that this kind of attack has a certain sequence of bytes in here from that shell code. If we see a packet with this sequence of bytes in it, we think it's an attack. So that would be a signature. We might also say in the ping of death, if we see an ICMP packet with a length field bigger than 64,000, we think this is a ping of death, and so that is a signature that says this is a dangerous packet, we should treat it as an intrusion. And here you can flag the packets, drop them, do what you want. And there's some language for describing what the signature is, like regular expression. Something that's very fast, so you can do it at gigabits or tens of gigabits per second. The other thing which is very attractive is called anomaly detection. And it says that attacks are sort of unusual things that don't normally happen. So what we want to do is look at good traffic when we're not being attacked. And then we want to say when we see traffic that doesn't look like our good traffic, that looks anomalous because it's doing something different. For example, normally we don't get port scanned. If we see traffic from a host that's connecting to every possible port, that's unusual. And so if something's unusual, we treat it as an intrusion, and then we can either prevent it or we can notify somebody about it. But the key thing is that in anomaly detection, we don't know in advance what attacks look like. We have to learn what attacks look like by learning what normal traffic looks like first, and then saying things that aren't normal are considered attacks. So in that sense, signature-based attacks will sort of let you defend against things you know about. If there's a new attack, it's pretty useless. Anomaly detection can work well because you don't have to know what an attack looks like to defend against it. You just have to know it looks different from what you're used to. So we'll go into more detail on a couple of these. Any questions? Yes?
Can this be used in tandem with each other?
Yes. And, very often people will use a firewall, which is sort of fast and cheap, and then they'll combine that with an IDS or an IPS. A lot of machines that you can sort of buy a network appliance, you plug in, and you put your Ethernet cables into both sides, and a lot of them can have a software setting that says, do you want to do detection or prevention? And it's just sort of a setting that says when you see an attack, what do? Do you log an alert or do you respond somehow at the same time? Because it's the same functionality, it's just what the response is that's different in the two cases. It also depends on how you configure it, because if you want to do intrusion prevention, you sort of need to have your box right in the middle, because you need to be able to sort of stop the traffic going through, right? So you need to make sure if there's some intrusion that your server doesn't see that bad traffic. On the other hand, if you're doing intrusion detection, it's okay to sort of see a copy of the traffic. We can just let our traffic go through full speed to servers. We can send a copy of it to our intrusion detection system, and our intrusion detection system can take as long as it wants. It's not going to slow anything down. So, we can have a whole bunch of machines here if we want to sort of handle lots of traffic. And this can take, seconds or minutes to detect an attack if you wanted, because we're not actually slowing traffic down. So they have different properties that they need. So intrusion prevention firewalls really need to run at full speed because you don't want to slow down access. Intrusion detection can be a lot slower because you don't have to stop the packets from getting to your servers. Any other questions? Okay. So in terms of these services, there's sort of a taxonomy of how they work. So we talked about one taxonomy, one choice already, which is whether they're policy-based, sort of using known signatures, or whether they're anomaly-based. Another question is, where do they run? This came up on the midterm, which is sitting right here, by the way, in case you haven't picked it up yet. Should they run on your end host, or should they run in the network? The action that they take, we mentioned already, should they detect an anomaly or an attack, or should they try to prevent something? And then there's the semantics. What level of information do they operate on? Do they operate at the IP layer, where we just see packets, source and destination? Do they operate at the TCP level, where they actually have access to the data contents? Or do they operate at the application level, where they sort of see application level requests and know application level semantics? So there's a lot of examples of each of these. So for example, Tripwire is an example of a host-based, rule-based intrusion detection system. It will sort of, tell you if it looks like somebody's trying to break into your host. A personal firewall, such as is available in Mac OS, is a local intrusion prevention system that's host-based. Snort is a rule-based intrusion detection system where you can sort of configure, here's what various attacks look like, raise an alert if you see them. So there's a lot of different combinations of these out there depending on what you're looking for. Okay, so we'll start off with, yes? When you raise an alert, so have you ever used, have you used like antivirus software, right? You get an alert, and sometimes you get an alert, and a lot of times antivirus is really preventative, right? Because it will stop things from happening, but it could raise an alert and say, it looks like you're under attack, what do you want to do? Raising an alert could mean you are writing a log to your system log that you can then look at later to sort of figure out what happened. It might mean paging an operator and say, looks like the system's under attack, and then a human can come in and start looking at logs and look at information. So alert, I think what you're getting at is that if you get an alert, it's really hard to know what you should do, right? And so that is why, systems that actually do something on their own are very attractive. Because you would like to respond quickly before you're actually compromised, but then you have to sort of understand the situation and do something about it. Okay. So firewalls have sort of two goals. One is that we want to sort of block attacks between hosts and services. So we want to sort of say if there's known attacks or known vulnerabilities, we want to block those by preventing communication to certain ports or from certain address ranges. We also generally just want to control the traffic. So if we have our demilitarized zone and then our secure zone, we want to really control, for example, what direction you can go pass through and make connections through that demilitarized zone, who can initiate connection. right? I mean, I said that, for example, hosts on your inside secure piece can call outward into your demilitarized zone. Well, as you know, when you communicate, you have to send packets in both directions. So you can't just say, we only let packets go out and not come in. We need to let some response packets come back in. And so our firewall has to have sort of rules to sort of control that, you know, if you create an outbound connection, then you can allow the incoming packets to come back, things like that. So from a logical viewpoint, firewall is really kind of partitioned the world into two views, that outside the firewall and that inside the firewall. And then generally what's on the inside of the firewall, we might have lots of hosts on the inside of the firewall that communicate with no extra security. But if they try to go outside, there's this one boundary they have to go through. So when a packet comes in, it's a somewhat straightforward choice. You see a packet come in, you can choose to either allow it to come through, you can modify it somehow, you can block the connection or the packet by dropping it, sending a rejection notice to tell the sender that you don't accept their packets. You can also queue the packet to have some more inspection happen later. Because it might be that you can't tell immediately, is it a safe packet or not a safe packet? You want to do something more with it. So in terms of placement, one option is you run it on the host, and then your host has a sort of a personal firewall here. The benefit here is that it's sort of faithful to your local configuration. So if you know what services you're running on your machine, your firewall can be configured to allow those services to work and block everything else. If you have a firewall that's outside your machine, then it's protecting lots of machines. And if any machine is running some service, you might need to allow access to that. So it can sort of be more closely tied to your particular host. If you're running older software that isn't patched, you might need to sort of close off extra things. Also, if you travel with your machine, you know, you take your laptop on a vacation somewhere, it travels with you. A network-based firewall has the advantage that if you have a lot of machines on your network, you only need one firewall instead of lots of firewalls. And it can make decisions based on all the traffic. So it can look for anomalous patterns that sort of span multiple different hosts in your network, not just what is happening to a single host. So if somebody is sort of scanning all the, doing a scan of the entire range of addresses, you might be able to see that with a firewall at the network level. You wouldn't be able to see it at a host-based firewall. Okay, so deeper into our taxonomy, there's a couple of sort of types of firewalls from least complicated to most complicated we talked about before, and there's also sort of policies. Default allow, which says any packet we don't have a reason to suspect we are going to let through, or default deny, which says we know exactly what traffic we want to let through, we're going to block everything else. So to sort of understand these options, remember our protocol stack, we've got our physical layer at the bottom, we have this, which is, you know, our fiber optic cable or our wireless air. We then have our link layer like Ethernet or 802.11 where we're sending packets with MAC addresses. We then have our network layer of IP, transport layer TCP UDP where we actually have streams of data and port numbers, and then our application layer SSL, HTTP, things like that. And so, you know, the thing to remember is there's sort of headers, and each of these things have headers. So TCP is going to have a header on its data, which is preceded by the IP header, preceded by the Ethernet header. And an application message may be split across multiple different packets, TCP packets or IP packets. So a very simple firewall is a stateless firewall, which says it really remembers nothing. All it does is look at the packets as they come by and say, for each packet, do I allow it or I deny it? And so what it can look at here is really sort of the standard header fields that have to be on every packet. So it can look at the IP fields like source and destination IP address. It can look at the protocol fields like TCP or UDP. It can look at the flags. Is this a SYN packet or an AT packet or port numbers? It can't sort of remember anything. So it's very hard to know when a packet is going, you know, to sort of allow packets to come back only if they're in response to something you sent out. Because it's hard to know. You can't remember, did somebody on the inside establish a connection and this is a response, or is this a new packet coming from the outside that I don't know about? So what you can do here is say, you know, simple things like I only want to allow traffic on port 22 for SSH and I want to block all other traffic. So that would be fairly straightforward by just allowing TCP traffic at the port field and TCP traffic in the protocol field and then the port number. You can also say I only want to allow SSH traffic in from a particular host. So if you know where your operator SSH is in from, you can restrict only giving SSH access to that one IP address. So it's not useless, but it's sort of limited in what policies you can express. The other thing is you can express sort of default deny policies here, because once you say I'm going to allow certain kinds of traffic, you can then add rules, and these are very much like access control lists, where you can deny all other traffic. So in this example, it says we're going to allow UDP traffic to port 53, on port 53 to some host. This is our DNS server, but then we're going to deny any other access to that port number or connecting to anything else. So this says you can only connect to a single DNS server here, but nothing else, because there's nothing else we should be connecting to, so we're just going to block it completely. So when we get to TCP-based protocols, though, we really want to have state. And the reason is we want to sort of know what state the connection is. We want to be able to reconstruct the data that's actually being sent, because TCP sends a stream of data, and the data might be in multiple packets. So, for example, we might want to have a policy that says every SYN ACK packet has to be in response to some SYN packet. This says that our packet is a response to a packet that originated on one side of the firewall. It's not sort of an unknown response, it's probing our network. To do that, we need to remember that we saw a SYN packet, and we need to know the sequence number in that SYN packet to know that the ACK corresponds to our original SYN packet. So, what this means is we need to start storing additional state. So we need to have state about the packets that we've seen, and we need to have rules on how we maintain that. Because suppose I send one packet and the firewall expects another packet and never comes. How long should it wait to hold on to that data for? Should it wait a second, a tenth of a second, an hour? Because if it doesn't wait long enough, legitimate traffic might get blocked because it doesn't remember the older traffic. If it holds state for too long, it might run out of memory and not be able to scan things anymore. So in this example for the TCP handshake, what we would do is when you send the SYN packet, the firewall will record the sequence number that the client sends on a SYN packet. When it sees a SYN ACK packet coming back, it's going to verify that the sequence number in this packet is the expected sequence number that the client sent. So it can verify that the server is sending the expected packet here. It's not some random server that's trying to do IP spoofing or something like that, that's trying to connect back. So far, so good? Okay, so this means in this case, we have what's called a stateful firewall. So the benefit of this is that it's more expressive. We can have policies about protocols and about the state of a protocol and whether messages are expected or unexpected. The downside is that we now have what are called state holding attacks, where we attack the feature of the firewall that says hold on to state, because we can try to sort of blow up the amount of state that it's saving and make it exhaust its space. The other problem is that the firewall, by holding state, has to sort of know what is expected. If there's any ambiguities in the protocol or in how the client behaves, the secure machine on the inside behaves, the firewall may not know what's expected anymore. And so if there's ambiguities, it may not be either, it may make the wrong decision about what is legitimate, or it might decide that illegitimate traffic is in fact legitimate because of this misunderstanding. And so we'll see some examples of that later. So the final kind of firewall we're going to discuss is an application level firewall. And this is really a firewall that runs at the application level. So it runs at like the HTTP level where it can see everything. People, for example, build TLS firewalls. Does anybody here have an Amazon Fire tablet? One person. So Amazon Fire tablets, the browser on that, when you make a web connection, connect to any server, their connection always goes to Amazon first. And then Amazon, from their servers, will go and connect to whatever web server you want it to go to. And this means that Amazon can sort of compress the data. There's people done looking at work at sort of recompressing videos, compressing pictures to be smaller. They could do scanning for security issues. when you connect over SSL or TLS, the same thing happens. You actually connect to a machine at Amazon. They do a man-in-the-middle attack for you to give themselves access. They sort of see all your encrypted data, and then they make a SSL connection or TLS connection to the actual web server. So this is at the application level, so they can see all of that HTTP information and make a choice on it. So in this case, typically applications will connect to the firewall directly, and then the firewall will connect to the end host. Or the end host connects to the firewall, and then the firewall connects to the server you're trying to talk to. And the firewall can then see all the messages and decide what to do. It can reconstruct the complete message and see things and has sort of complete information. So an example of this, as I mentioned, is sort of a web proxy where the web proxy sort of sits in the middle for all your access. So the benefit here is that you sort of know exactly what applications are supposed to do. You have sort of the complete information. You're not sort of subject to network level attacks about fragmentation and things like that because you see everything. The downside is that it can be slow because you're doing a lot of processing. And you also have to build, you have to know exactly how applications behave to make this work correctly. Any questions on firewalls? Okay, yes?
So if your firewall is like at the application level, have there ever been like historical attacks at the lower parts of the stack?
Yeah, so I mean, certainly the IP level attack, like MAC address spoofing, address poisoning works below at a lower level of the stack. TCP and IP fragmentation attacks work at a lower level of the stack.
But if people ever like hijacked like the lower part of the stack and like control things from there,
I mean, certainly by doing something like, by working at the lower levels through fragmentation attacks, DNS poisoning, ARP poisoning, you were sort of taking control of the low level of the stack of where packets are delivered, and then you were sort of getting the client to send packets to the wrong location where you can sort of completely control things. You know, in the example of the application level firewall, the packets are being delivered sort of, because they get to the firewall, they're being delivered to the right place. And so at that point, what the lower levels did wasn't that important because the firewall is now going to reconstruct the entire application level message, and it will then resend that message on a brand new connection that the attacker has no control over. Because that new message goes sort of between the firewall and the inside host, and it is generated by the network stack on the firewall itself. So all of those messages are sort of not impacted by what the attacker did. If you have a model where you're actually reconstructing things but forwarding the original packets along, so you're not what's called terminating a connection, you're just sort of reconstructing application state, then there might be vulnerabilities that could get through. And we'll actually see some of those in a minute. So this is sort of the configuration you might use to set up a DMZ, with an exterior firewall that allows traffic to your DMZ, and then an interior firewall that allows traffic from the DMZ to the inside, or from the inside into the DMZ to push content there. Okay, so enough on firewalls. We're now going to move to more sophisticated intrusion detection and prevention systems. So the logical viewpoint is pretty much the same as a firewall. You've got an outside, you've got some box that your traffic is flowing through, your IDS or IPS, and then you have the inside. And what you want to do with this box is the same thing that a firewall did pretty much, which is either report that there's some anomalous message here. If that's an IDS, if it's an IPS, you might drop the packet or log that there was a suspicious packet. You can allow the packet to go through, or again, you can queue the packet for further processing. So, pretty much the same set of things we saw before. So if we look at our taxonomy here, we're going to again have sort of this policy versus anomaly, network versus host, detect versus prevent. And here we sort of get to look at the semantics in terms of how deep we look. Again, are we going to go up the application stack or not? So a policy-based IDS is really going to have sort of handcrafted policies that say, what do we not allow? So these are some predetermined set. You can download them off the internet. You can write them yourself. People have looked at research where you try to monitor traffic and then automatically generate the rules to use in an IDS. And these can either be regular expressions where you can sort of say what the traffic looks like as a regular expression. It can also be a cryptographic hash that says my attack packets have some particular hash. So here are some examples. The first one is, we worry about fragmentation attacks. Fragmentation shouldn't normally happen. So we're just going to say if we see fragments less than 256 bytes, we're going to treat this as some kind of intrusion. And so the rule would say if we see, TCP traffic from any source, any port, any destination port, with a minimum fragment of, we're going to specify a minimum fragment size of 256, and we're going to raise an alert, tiny fragments detected, possible hostile activity. So this is a rule that will detect potential fragmentation attacks. It doesn't do anything because it's logging a message here, but you could consider also using this to sort of block such messages. So in a second example is sort of looking for a very specific overflow. So this is really a signature of what an overflow packet looks like. So here we say we are looking for traffic over TCP from any source to any destination on our network, 192.168.1.0, port 143 with the content of these particular bytes /bin/sh. So that is our shell code that is going to be used to sort of do a buffer overflow and take control. And so this will, if packets come in looking like this, it will raise an alert saying I'm at buffer overflow detected. But again, the idea is that we're writing signatures that say what does bad traffic look like, and we are trying to match those signatures. So the key challenge for an IDS is how do you very quickly match, hundreds, thousands, tens of thousands of signatures, because you want to detect all known attacks. And how do you do that very, very quickly? So you're looking at, gigabits of traffic per second, tens of gigabit per second. So doing that very quickly is challenging, and having so many rules and getting the rules updated quickly is a challenge. Seem reasonable? This could be your job, writing IDS rules. So this applies, and this is a quick digression, this same approach applies not just to networks, but also to operating systems. So people have applied the same kind of intrusion detection to operating systems by saying, do we see sort of unexpected behavior in an application? So the model that this paper took was to say, let's look at the set of system calls an application makes, and we're going to sort of make the call graph of an application into a state machine. And we know, for example, in your function, if you call open and then you call close, then we know that we should see calls to open and close always in that order. If we see close first and then open, we know something's wrong. So we can build a state machine from an application to sort of say what it looks like. And then as an application executes, we can sort of walk that state machine and see, is this system call expected, that it's allowed by the state machine? Or is it unexpected, that there's no transition that takes us to a state where the system call can happen? If that happens, we can then raise an alert that says this application was compromised. So this is a use of a stateless stateful intrusion detection system that has a host base, but it's looking at the system call level instead of looking at the network level. So these ideas can work at all different levels, is kind of the point here. And you can see the value of state here, because we're not just saying, is there a system call that shouldn't be made, but we're saying, is this system call that is normally allowable something you're allowed to call at this point? Okay, so that was rule-based. Let's now look at anomaly-based intrusion detection. So the idea is that we have some sequence of events. Think about every network packet coming into your network. There is some distribution of normal events that says, there's short packets, there's long packets, there's packets that come very tightly packed, there's packets that spread out. We get a lot of HTTP packets, we get some TLS packets, we get some UDP or DNS packets. So there's some distribution of packets that we look for. And then occasionally we get some sort of anomalous packet indicated by this lightning bolt here. And the goal of an IDS is to sort of look at this packet and sort of say, does this traffic that we're seeing fit into the normal distribution of what we expect, or does it look anomalous? Because we haven't seen it before, we don't think it should be happening. So as I mentioned before, the beauty is you don't have to know what an attack looks like, you just have to know what normal looks like, and anything abnormal could be an attack. So one example is, suppose we have a server named Alice, and Alice normally connects to a bunch of different machines, Spark, XKCD, /.reddit. These are what she normally connects to during her average workday. Most of her work is done inside the network, so we don't see those. These are the external connections. If we see this on the first 300 days, and then on the next day, we see connection to the machine 18487, we can kind of say, this looks anomalous. Alice never connected to this before. She's been pretty consistent on these other 4 machines. This looks like an anomaly. Maybe she's been attacked, and there's some rogue software. Somebody took over a machine that is now trying to attack. So this is the kind of anomaly that we can look for, where we see a deviation from normal behavior. And this is a simple one, this working set model that says, we have a standard set of machines you access. Are you accessing some server you've never accessed before? One thing to, yes?
There's some ways to, because I can see how false positives could spring up from that kind of situation very easily. Is there some way to mitigate false positives?
So you can. So this is a very simple model. So what you could say is, if you're looking at what normal users connect to, it's very hard to sort of build up a set of everything you connect to, because many people will go to new servers every single day. If there's something on Reddit, there's something on Facebook somebody links to, you go there. What you can do is you can say, normally when Alice connects to a new machine, she interacts with it once or twice. And here we see, very high frequency interactions spread out throughout the day. And so it's not just the server that's different, but it's actually the pattern of behavior. So you can go by more than just the server identity, but sort of what the traffic looks like as well. So if we go back to our pros and cons, the pros are, you don't have to know the policy. You can find unknown attacks, which are called zero-day attacks. These are attacks where there is no sort of notice that this attack exists and you can defend against it. It's sort of a secret until it's actually used on you. The con is that you have to have an attack that does not look like your known traffic. Whatever you are detecting about your known traffic, the attack has to look different in a pretty substantial way so that you can see it. If somebody figures out a way to make an attack look like totally normal traffic to you or to your anomaly detector, it'll slip right through. And the other problem is that learning this distribution of correct behavior accurately turns out to be difficult. So we'll dive into that a little bit more. So the next thing is, okay, we have IDS, IPS. How do we actually get around these things? Because as we know, there are no perfect security mechanisms. So these are not perfect either. They're an engineering trade-off of what is fast and what is cheap against what is secure. So we'll first look at a state holding attack. So I mentioned this before, and this is the case. We have a stateful firewall or IDS. It has to remember things about every connection. So remember, for every SYN packet that was sent, it has to remember that SYN packet and the sequence number so it knows if it sees an appropriate response. So if I send a SYN flood, this is going to make the firewall allocate a lot of space to keep track of all these packets. This was the same exact problem we saw with SYN floods just on ordinary hosts, but now it's the firewall. And the difference is, if we can knock out the firewall, two things happen. One, if we knock it out, it shuts down all traffic to that, everything behind the firewall, so we have knocked out an entire company to some extent. Or it fails open, which means when it goes down, if it's an intrusion detection system that's sort of offline here, there's no intrusion detection anymore, and then we can do other attacks that won't get seen. So we can sort of open the turn off detection for a while so we can launch new attacks by overwhelming it. So another thing we can do is fragmentation attacks. So I mentioned this before, I'm going to go through a little bit more. So we have data, we can sort of fragment it, we can sort of break it into fragments, and now we can see that the firewall has to figure out what is the host going to actually see if there's fragments. So there's a couple of problems. One is that the signature it's looking for might be split across multiple fragments. So this is just an example of how fragmentation works. So for example, suppose we have a policy that says, allow traffic to port 80, which is HTTP, don't allow traffic to port 22. So we are going to sort of take our traffic, packet 1 says source destination port 80, but it's fragmented. And so we're going to send another fragment where we actually overwrite the port that it's going to with port 22. So this means that the firewall that saw the first packet, may not be able to compose these two packets together. So if it let the first packet through, it doesn't really know what to do with the second packet. And so this means that the packet that we actually send through the firewall will have the bad port number because the port number was split in a separate packet from the TCP header, the rest of the TCP header. So this is an example of why you need to sort of queue packets and delay them until you can reassemble fragments so you can see exactly what the destination host is getting to. But that opens you up to a resource exhaustion attack. So this puts the firewall or IDS or IPS system in a difficult position. Another thing you can do, yes? Yeah.
Is that because when you have tiny fragments, you might have just queuing them and you run out of space?
Right, exactly. That you can just send lots of fragments that the firewall has to hold on to try to rebuild them. So a firewall, this is where having a rule that says just don't allow fragments could help, but that means there's some legitimate traffic that does get fragmented that would be broken. But yeah, the idea is if you send lots of fragments from different connections, they'll all get stored in memory. Once you run out of memory, it can't filter anybody else's traffic. So this is another attack. Here we're taking advantage of the time to live field inside an IP packet. So a time to live field basically is it's a field that says how many times are you allowed to send this packet through a router. And the idea is that if you have some kind of loop in your network, you would like the packets to expire instead of going around in this loop forever and ever and ever using up resources. So every time you send a packet to a router, the router decrements the TTL field, and when it gets to 0, it's allowed to drop it. So we can use this as an attacker. Suppose we send some packets, and we set a TTL field of 12 on one packet and 20 on another packet. If the IDS or firewall sees the first packet, it'll say, oh, we're connecting to nice, that's great, we'll allow it to go through. When we see the second piece, it's a fragment now, so we're not so worried about fragments. Or we know that the fragment will be dropped because the first packet goes through for some reason, but it has a higher TTL and actually makes it through the end. So the key thing here is that the system here doesn't actually know, the IDS system doesn't know what the end host will see because it doesn't know of these packets which will actually make it all the way to the host, which will get dropped someplace else. Right, because it sees the good traffic and it thinks that it will get there and overwrite the bad traffic, but in fact the good traffic is dropped. So the other problem here we talked about before is fragmentation overlap. When you have sort of multiple packets here, the way that the firewall looks at overlap may not be the same as the host. So packets could get reordered and be delivered in a different order. It could be also the host has a different policy of what to do when you get fragments that overlap. And so the firewall may say, well, I see ATT, A, ICK. I'm going to assume the I overwrites the A. It's not an attack sequence. That's fine. Whereas the end host might decide to drop the I packet instead and actually gets attacked. So again, the challenge here is that the firewall or the IDS sees a different set of traffic than what the end host actually ends up receiving. So a fix for this is to have some kind of traffic normalizer that says, instead of trying to figure out what is legal and reconstruct everything, we are going to basically take all the traffic that comes in and then normalize it somehow. So we are going to, fix all fragmentation problems and reassemble things. We are going to set all TTLs to be exactly the same value. Anything where there's ambiguity, if we see two packets that overlap, we're always going to drop one of those two packets so that we never have this ambiguity anymore. So we are going to take whether there's multiple things that could happen, the normalizer will sort of remove that and just have one stream of traffic that is unambiguous how it gets delivered that comes through and that has been scanned. So this is nice, but of course it adds cost and complexity and there's a potential some things could break. So the key problem that affects IDS systems is that, you know, they see a different view of traffic than what the host sees if it's out on the network, and the view that they see may not be correct. And they may resolve ambiguities differently. So this is somewhat of an argument for having a firewall on your host also, in that it actually sees the traffic going to the host because it's at the same location, so it's seeing exactly the same traffic. In the network, you're seeing some other piece of traffic that is similar to what the host gets, but not the same. So a final attack here is called an algorithmic complexity attack. And this is really sort of a attack where you try to use up the CPU of the firewall and sort of slow it down. So the idea is if you have a stateful firewall, it's going to be maintaining information about the connections that it's on. It probably has a hash table. And normally in a hash table chaining, you know, you have a nice distribution of packets, so you have, you know, very fast access to all your data. However, suppose you're an attacker and you know what firewall somebody is running and you know the hash function they use. Is there something you could do to your traffic to subvert this hash table? Your, you know, hash tables are designed for nice distribution of data, for nice users of hash tables. What can you do as a malicious attacker to abuse hash tables? Right, so you could say, I'm going to guarantee that every packet I send will collide in the hash, and so it actually turns into a linked list, right? So if you send 10,000 packets and end up in a linked list, and every time the packet comes in, you need to search that linked list, that's a lot of CPU to be used, right? And so this can overwhelm the processing capacity of the firewall, and then again, either you sort of shut down the network as a whole, or the IDS, if it's on the side, gets turned off and stops detecting problems. And it will sort of start dropping packets because it can't keep up anymore. But again, the idea is, you know, here we're going to sort of abuse the assumptions that programmers make about benign distributions and nice, smooth, you know, people who are not trying to subvert the system and try to subvert the data structures. So that is it for sort of how firewalls and IDSs work and for how to sort of defeat them. I now want to spend a little while talking about why anomaly detection is hard. Before I go on, any questions? Okay. So, you know, the question is, can we do realistic anomaly detection? And what this really means is, given sort of, you know, a mix of normal events, can we reliably detect what is anomalous? And how accurate does our detector have to be useful? So we're going to do sort of a formal approach to answering this question. So we're going to start out with omega. Omega is the set of all possible events. So in a firewall, it's sort of the set of all packets that you might see. On a host, it might be all the log records in your syslog that you're looking at to detect if you have been, if there's been an intrusion or not. This is the world of all the things that you see. Within this, we have set I. These are the actual intrusions where somebody has broken into your system or is trying to break into your system. This is what we're trying to detect. This is what we're trying to prevent. So far, so good. So we can then calculate the intrusion rate, which is the number of intrusions divided by the set of all possible events. This is sort of the probability that a given event is an intrusion. So if we get 1 billion packets and 1 million of them are intrusion attack packets, then our probability of an intrusion on a given packet is 1 in 1,000. So this, you know, tells us roughly how many bad actors are there out there in this world. And our goal is, of course, is to find all of them. Okay, so we then have a set of alerts. These are the alerts that your system will find. And the alert, there's some alert rate that says, given all these set of events that we have, how often do we raise alerts? So, you know, on those 1 billion packets, we might raise 1,000 alerts, we might raise 100 alerts. So if our intrusion detection system is sound, that guarantees that all the alerts we raise are actual intrusions. This says the set of alerts of things we alert on is a subset of the things that are intrusions. So we have no false positives where we're generating an alert that is not an actual intrusion, although we are missing some of those intrusions. Likewise, we have complete. Complete says that all the intrusions have an alert. So if we have a complete system, we know that every single intrusion generated some alert, although we might have extra alerts for things that were not actually intrusions. So a false positive then are the things that are alerts but not intrusions. A true negative are the things that are neither alerts nor intrusions, things that are outside of these two ovals. False negatives are when there's an intrusion and we didn't detect it. So this is the set of intrusions I, and then the complement of all the alerts that we generated. And then we have true positives. So this is the set of alerts that were actually intrusions, and intrusion, the intersection of the set of alerts and the intrusions that we get. So clearly what we want is we want I and A ovals to sort of completely overlap in a good system. And one of the things as a designer you can choose is how, given the options, how close do you get to that? And do you want to fail by having too many alerts, or do you want to fail by missing some intrusions? Because they have different trade-offs. So the detection rate then says, what is the probability, given that I have an alert, that it's actually an intrusion? So this is the probability that there's an intrusion, or the probability that I saw an alert, that I'm sort of in this middle section, and divided by the probability that there's an intrusion. This is the probability that there's an alert given there's an intrusion. This will tell us what fraction of intrusions we actually detect. Right? We would like to detect all the intrusions here. So graphically, what this shows us is of the intrusions, this I, what fraction of them are actually in that true positive space. So far, so good? Okay. Yeah, so it's the, these are the intrusions that raise an alert. Okay, so let's sort of go through an example and see, how we do this. Suppose you have 1,000 people in the city. This is a reduced version. There's only 100 people in the picture. Suppose one is a terrorist, and we have a face scanning. We have their pictures. And what this means is that the base rate, this is sort of, we know background information that 1 in 1,000 people in our city is a terrorist. So there are not many terrorists around relative to everybody else. And now we have a facial recognition system, and it has these properties that it's 99% accurate. This means that 99% of the time, when it looks at a face, and it's a terrorist, it'll sort of correctly detect that person as a terrorist when that person is a terrorist 99% of the time. And 1% of the time, when it looks at someone, it'll say this is a terrorist when the person is not a terrorist. So that means for every 100 good people, the alarm goes off just once. For every 100 terrorists, it goes off 99 times. So now we want to sort of figure out, how good is this? If an alarm went off, is the person that we detected actually a terrorist in the system? And I think most of you have an intuition what's going on here. So one way to answer is to say, well, the facial recognition system is 99% accurate. That means there's only 1% chance that the guy that we detected is not a terrorist. Is that believable? Yeah. Good, good. You're all skeptical about such claims, as you should be. So the problem is we have to think about all the times that it goes off when it's not a terrorist, because most aren't terrorists. So to sort of formalize it, we're going to say the base rate probability here, probability given a person that they're a terrorist is 0.001, 1 in 1,000. We can now formalize how good the face detector system is, because we can say, 99% of the time when we detect someone as a terrorist, they are. So this is probability, given that we have an alert this person is actually a terrorist, is 0.99. That is what it means to be 99% accurate. And probability of an alert, given that the person we're looking at is not a terrorist, is 0.01. Because this says 1% of the time we're going to look at somebody who's not a terrorist and raise an alert anyway. What we want to know, as I said before, is what is the probability that we've actually caught a terrorist when we get an alert? Because this will tell us, do we want to go capture the person right away, or do we want to, go and talk to them and learn more? It tells us, is it likely to actually be the person we want? So intuitively, what you can sort of expect is that we're going to have a bunch of false alarms here, because we know that there's a lot of people who aren't terrorists. We're detecting some fraction of them as being terrorists. And so we actually want to know more specifically what fraction of the results we get are going to be false alarms. So our intuition is that, given 999 good people and a 1% error rate, we're going to have something like when we scan all 1,000 people, we're likely to get 1 terrorist and 9 to 10 false alarms when we falsely identify a good person as a terrorist. Okay, so let's get to the math. So we have these various probabilities. What we want to do is calculate the probability that if the terrorist gives an alert. So this is the probability that it is a terrorist and an alert happened divided by the probability that there was an alert. So we now have to figure out what are these probabilities. What is the probability that there was a terrorist and we got an alert? And what is the probability of getting an alert on a given person overall? So we'll go through these. So the probability of it being an alert and a terrorist is the probability that we get an alert on a terrorist times the probability that the person is actually a terrorist, right? So we're basically taking these two sets and multiplying the probabilities of these independent sets. So we have this information. The probability of being a terrorist was 0.000001. The probability of an alert given a terrorist is 0.99. So we can now calculate the probability. The intersection probability is going to be 0.0099 or something like that. So the second thing we need is what is the probability of getting an alert overall? So there's two cases when we get an alert. Either we got a real alert because it's a terrorist. So we just calculated what is the chance of that happening. The other time we get an alert is when it's a false alert for someone who's not a terrorist. So this is the second piece here, which is the probability of it not being somebody not being a terrorist times the probability of getting an alert when they're not a terrorist. So not being a terrorist is 0.999. The alert not being a terrorist was 0.01. So we can sort of combine these, build a nice big garish formula that sort of tells us what to expect. And if you sort of do the math, you end up that about 9% of the alerts you get are actually for terrorists. So this is, remember, we have this 99% accurate. Our intuition that we have 9 or 10 false positives was spot on in this case. So the thing here is it says when you're detecting anomalies, if you don't want a lot of false positives, you have to have a very, very accurate detector. If your sort of true attacks are rare. If your attacks aren't rare, things can be different. Suppose, for example, we made our face detection system 10 times better. So it only failed 1 in 1,000 times. In this case, we still have a 50% chance of somebody we detect as a terrorist not being a terrorist. It's only a 50% chance when we detect someone as a terrorist, they actually are a terrorist. So this, again, is the challenge here, that we need to have a good way of dealing with this, or we need to accept false positives. So this makes anomaly detection difficult to deal with, because if the events are infrequent, most of what we get alerted will be a false positive. And what happens to humans when they get a lot of false positives, right? They stop paying attention, they get annoyed, they complain to their boss, they turn off the intrusion detection system because it's always a false positive. And so keeping your false positive rate low is important because those false positives take a lot of cost and energy to track down. But at the same time, you need fairly high accuracy to actually make sure you're not missing the true attacks. So the takeaway is, you can easily learn things that are pretty common and frequent. It's hard to sort of learn about rare but legal events. There's sort of a lot of diversity of what could happen. You may not learn it, you may not learn it well. And sort of deciding between rare but legal events and illegal events can be very difficult. So this means if you're deploying this, you really have to figure out how bad are false positives for your organization. What can how much are you willing to detect, sort of deal with? So for example, when I run antivirus software on my laptop, every day or two I get some pop-up saying it found something. And I have no idea if those are false positives. The cost to me is fairly low, that they rarely interfere with what I'm doing. If it actually blocked me from getting to useful websites, you know, 1 or 2 a day would be enough that I would turn it off and I would take the risk of not having antivirus software because the false positives would be too annoying. So that brings us to the end of our networking section. In conclusion, we talked about firewalls that were sort of stateless packet filters or stateful filters that could reassemble protocol information or application level firewalls and proxies. We talked about where you put them, the idea of a demilitarized zone that separates your sort of inside of the network and your outward-facing servers from the rest of the internet as a whole. We talked about anomaly-based detection versus policy-based detection, that policy can be very accurate, but it misses things you don't know about. Anomaly can find things, but you're likely to have a lot of false positives. We talked about how to evade these things through sort of network-level attacks, like fragmenting things, using TTL fields. We talked about sort of overcoming the firewall itself through resource exhaustion attacks of CPU and memory. And then we talked about sort of the difficulty or sort of thinking about how good does your anomaly detector have to be to actually not have a lot of false positives. Yes?
One popular way to get around firewall detection is just the direct attacks in general. So, like, for example, like the classic, you generate an error and the error is formatted in such a way that when it's put into your log server on your inside, that causes like some sort of exploit.
Mm-hmm.
So, like, are there other big things that fit into that, or?
So the question is, are there things where there's something that you can, sort of an indirect attack where you sort of do one kind of request which is mostly legitimate, doesn't get stopped against the server, that causes the server to do something unusual that will sort of trigger a vulnerability in someone else. So those are difficult to pull off, to sort of do that two-step thing. I mean, to some extent, the way that's more common is that you have some way of attacking a system that the firewall doesn't know about yet, and then you can remotely log in and, you know, get a shell or something like that and use that to sort of directly attack things. You know, I guess another case that happens, like SQL injection is an example of that, where you're sending some SQL code, it's HTTP traffic, it passes your firewall, but then it causes the application server to do an attack on your database and like delete all the data or expose the data or something like that. So that is some example of how you can defeat firewalls. If you had an application level server that understood your application, it could look for SQL injection attacks or cross-site scripting attacks and sort of strip those out and prevent it. But at the network level, that's very difficult. Any other questions? Okay, well, great.